I'm Guillermo Castilla and this is AULA UE. Today we're going to be explaining a bit about the normal distribution. As you already know, the normal distribution is a continuous model, and what it really tries to explain is how to calculate probabilities inside something that distributes, let's just call it normally, with open quote, close quote, probabilities. For example, if I want to know the probability of being smaller or equal than a certain value, let's say 3 for example, in a normal distribution, well, it would be difficult to calculate at first because the normal distribution does have a known density function, but the density function isn't very easy to use. So instead of that, what we're going to use is another normal. Now, this might be a bit strange, but in this case the probability of x being smaller or equal than 3 in our original normal, mu sigma, is the probability of z being smaller or equal than 3 minus mu over sigma in our normal O1. Now, that value we can now obtain from a certain normal value table. What you might wonder is exactly how this works, and this works for a very, very simple reason. Every single normal, whatever the value of mu and whatever the value of sigma are exactly the same. They're just bigger or smaller. Okay, mu just tells us where it is centered. As you can see in the 0, 1, it's centered in the 0, and in the mu sigma it's centered in mu, and the sigma tells us how big the distribution is, how wide it is, but really it's just a factor of scaling it. It is the same distribution. So in this case, if we have the value 3 and we want to see what the value of x is smaller or equal than 3, then we'd have a value alpha in the other normal, and really the probability, which in this case this would be the probability of being bigger or equal to 3, and this would be the probability of being bigger or equal than alpha, would be a in both cases. Okay, because that probability, the area below the curve in both, is going to be exactly the same as long as z is equal to 3 minus mu divided by sigma. When I say 3, of course, it's any value of x we want. Let's put an example, because this might be a bit messy unless you're actually seeing what we're doing. So let's say the probability of x being smaller or equal, let's use the same value, let's say of 3. Okay, see, yeah, there you go, 3. When x belongs to a normal distribution, let's use any normal distribution in this case, let's call it a 2-1 normal distribution, okay? Where mu, the mean of the distribution, is in 2, and sigma is in 1. Okay, this is just an example. We could use any numbers. The 3, the 2, and the 1 are just generic numbers we're going to use just to explain this. So z, in this case, when I use the 0, 1 normal, would be whatever the value we want of x minus whatever the value we want of mu divided by whatever the value we have of sigma. So that would be 3 minus 2 divided by 1. That's 3 minus 2 is 1, divided by 1 is 1. So we want the probability of z being smaller or equal than 1, and that would be the same as the probability of x being smaller or equal than 3. So the first thing we'd have to do is go to our normal 0, 1 table, which is this table over here. Okay, these tables are standardized. It's what we call the standardized normal table, and they're extremely easy to use. Okay, as you can see, and in case you don't see it, I'm just going to write it here bigger. This is the probability on this table is of z being smaller or equal than whatever number goes here. Okay, so we want the probability of z being smaller or equal than 1 in this case, and this one over here. So let's look for that on the table. How would we look for that on the table? Well, although you can't see it maybe, that is a z over there. and this vertical column over here, the colored vertical column, are the units and the first figure. Okay, the units and the decimals. As for the horizontal row, the top horizontal colored row, all this are the second figure. Okay, they are the centesimals. So in this case we want number 1. So number 1 is actually 1.00. So it would be, we look for 1.0 on the column and 0.00 on the row, and we'd find this number over here, and it gives us the probability of Z being smaller or equal than 1, which is 0.8413, as you can see over there on the table. So the probability of Z being smaller or equal than 1 is 0.8413. Of course, the probability of Z being greater than 1 would be the complementary of that. So what we have really is, what we've done is we were being asked what the probability of x being smaller or equal than 3 in a normal 2-1 is, so we passed it to a normal 0-1, which then the answer now was the probability of Z being smaller or equal than 1, and we calculated that and we got the 0.413. So let's see it in the table here. Okay, we had originally a normal, and we were asked a question. Okay, we had this normal over here, the one I'm painting. It's centered around 3. No, sorry, not 3. It's centered around 2. Okay, let me get rid of that. It's a 2 there and 2 there. Okay, it's a normal 2-1. Okay, and we're asked the probability of x being smaller or equal than 3 in that normal 2-1. So what we did is we passed from that normal 2-1 to a normal 0-1. Okay? Normal 0-1. Here we go. That's f of z, and here goes z. Okay? There you go. Okay, so now the probability of being smaller or equal than 3 would be here to the right of 2, and 3 minus 2 divided by 1, which is x minus mu divided by sigma, would be z. Okay, so 3 minus 2 divided by 1 is 1. So we have 3 here on the x1 and 1 here on the z1. And what we're saying is that the area on each side of these numbers is going to be the same. The area to the right of 3 is the same as the area to the right of 1 in each table. Okay? So what we're really being asked is actually the probability of x being smaller or equal than 3 and the probability of z being smaller or equal than 1. So the area we're calculating is actually the one that's to the left of the normal itself. So how does this work? Well, it's quite simple actually. We just go from the f of x to the f of z. There we look for it in the table, and once we've got the number, we know that the probability on both is going to be the same. So as the probability we saw on the table was 0.8413, the probability of our original problem will be the same. I hope you actually understood this and you found this useful. I'll see you soon in AULA UE.